So this will be the first course among the courses mentioned by Maxence, who asked us, and Sophie and myself, to give a rather elementary basic introduction to electromagnetic waveguide. So I will do the first part, and then Sophie, the easy one, and then Sophie will do the second one, the less easy one. So the outline of the third part will be the following. So in a rather informal way, I will give some generalities about waveguides and with a small zoom on the acoustic case to prepare the transition to electromagnetic waveguides, for which I will first give the mathematical formulations, the equations, and then in a second step, some of relevant mathematical results. And I will finish by a particular case where the electromagnetic velocity is constant, in which case we shall see that some particular phenomena occur. Okay, so for my general introduction, I will consider a rather general model in which the unknown, as you can see, is vector valued, is defined in a domain in space in subdomain of R3. So this is for the notation. Well, vector valued, and the model equation will be like that, where alpha is a positive coefficient, so it's dependent space, and L is a second-order linear differential operator with variable coefficients. I have written like this to anticipate the fact that later the one in the space direction, I call Z, will play a particular role. And I suppose that this operator is homogeneous in the sense that it contains only second-order derivatives, no lower-order derivatives, and that it is formally self-adjoint, for instance, really self-adjoint, in the sense that this bilinear form here is supposed to be, je ne sais pas, le pointeur n'a pas l'air de marcher, c'est pas très grave, symmetric and positive. So, and it will be clear on the two examples I am going to give. So the first example is for acoustic waves, which is a scalar model with the unknown is pressure, acoustic pressure. And the operator L is this div-grad operator with variable coefficients. And the bilinear form is simply the grad-grad bilinear form, which is obviously d'accord, ça va. Ah oui, is clearly symmetric and positive. And in electromagnetism, so I will consider that the unknown is the electric field, it's a choice, so it is vector valued. This time the operator is a curl-curl operator with variable coefficients, and the bilinear form associated to this operator, formally, it is this bilinear form, again, clearly symmetric and positive. Okay, so I will say that I have a waveguide if the model is invariant by translation, which means two things. First, the geometry of the domain of propagation of omega, which is supposed to be a cylinder. So I consider a perfect waveguide with cross-section S that I will suppose to be connected without loss of generality. And the second requirement is that the coefficients of the model are also independent of the direction Z of the cylinder. Okay, so this corresponds to, and if in addition the cross-section is bounded, which I will assume from now, we say that we have a closed waveguide. So it corresponds to this picture where I recap all the main notations already introduced. In addition, I will denote nu the normal unit vector outgoing to the cylinder. Ez will be the unit vector along the axis of the waveguide, and tau will be the vector which is tangent to the boundary of the cross-section. And of course, because you have a boundary, you need to complete the model by boundary conditions, and traditionally, it will be a Neumann condition in acoustics, or the so-called perfectly conducting condition in electromagnetic. So this is a tangential trace of the electric field. And in this type of geometry, we can a priori consider two types of problems. First, the evolution problem. So you look for the solution as a function of x and t, given initial data. Or the time harmonic problem, where this time you consider a given frequency, which is a parameter of the problem, and you assume that the source term, the right-hand side, it oscillates in time with the frequency omega, so that you can look for a solution of the same type, which is called a time harmonic solution. If you plug it in the equation of the model, you obtain what I call the generalized Helmholtz equation, if you want. So of course, you have no longer initial conditions, but you need some additional condition to well define the problem. And these conditions are radiation conditions which are supposed to represent the behavior at infinity of the solution. So I will not speak about that, but just for mentioning this important notion. So the two problems, as you can imagine, are related. For instance, if you apply the Fourier transform in time to the first problem, formally, the Fourier transform is a solution of the second one. And moreover, another way to see that is to say that the solution of the second problem will be the limit, or will represent the behavior for large time of the solution of the first problem, provided that the source term is time harmonic. Okay. So what is a guided mode? So a guided mode, for me, it will be a particular solution of the equations, which has a very particular form of this type, where the wave number beta and the frequency omega are a priori real, and we look for a solution with u different from 0, of course. And if you put this in the equations of the model, you obtain what I call the modal equations, so I don't, plus, of course, the boundary conditions. And which is important is that the operator that appears is L beta, and L beta is simply deduced from L by replacing the z derivative by the multiplication by I beta. Okay? And what you have to immediately to realize is that for such solutions to exist, you need some relationship between omega and beta, which is called the dispersion relation. So very formally, these dispersion relations can be expressed by the fact that you need that this operator here has a non-zero kernel, and so it is a condition on omega and beta. Okay. So since the operator L is of second order, you can expand it in powers of beta, and each of the operator Lk is of order k, as indicated here. And once you have put an appropriate functional framework, in particular an Hilbert space to work with, I will be more precise later, you will be able to rewrite this problem as a self-adjoint an eigenvalue problem of this type, A of beta equal omega square u, where the operator A of beta is an unbounded operator on H. It has itself an expansion in powers of beta, and typically the operator A2 and A0 will be self-adjoint and positive. The operator A1 will be its skew adjoint, and it becomes self-adjoint because of the high here. the contribution. So A beta itself is self-adjoint for real beta. Okay? And A0 is bounded because the operator L0 is over there. It is a general structure, I would say. And so you can adopt 2 points of view. Either you consider that beta is given real. So in that case, as we will see, it's more adapted to solving the evolution problem in time. We will see later. And you consider as the frequency given and you look for beta. So of course, it's more adapted for the problem omega where the frequency is given. And also, this notion of modes are important to define the radiation conditions I spoke about before. Okay. From the mathematical point of view, the problem 1 is relatively easy because it is a sequence of self-adjoint eigenvalue problems parameterized by beta. And the second problem is more difficult because so it's not really a general an eigenvalue problem. It's more a quadratic eigenvalue problem for an operator pencil. And because of that, all solutions will not necessarily be real. And by the way, as soon as A of beta is not real, A beta is no longer self-adjoint. These two remarks are related. So in an important case, in simpler case, is when the operator A1 does not exist, is 0, and the operator A0 is positive definite. And in that case, the two problems are more or less equivalent, because you remember that the first problem was like that. But if you multiply everything by A0 to -1, the second problem can be also written as a standard eigenvalue problem. So the difference is that omega square becomes minus beta square. The dependence of the operator with respect to the parameter is also very, very, very simple. The operator, as I say, this operator A of beta is self-adjoint, and the other one is also self-adjoint. You have just to change the inner product using the fact that this defines also an inner product. And another difference is that A of beta is always positive, but because this term is negative, the operator AT log omega is only bounded from below. Okay. And I will restrict myself to the case where the operator A2, the principal part, has a compact resolvent, which is a situation that will be met with a closed waveguide. So in that case, for solving the first problem, finding omega given beta, you have to introduce the spectrum of the operator A of beta, so it is a sequence of eigenvalues that goes from to infinity, and there are positive eigenvalues because you're in the compact resonant case, and a corresponding sequence of eigenfunctions which form an orthogonal basis. And once you have that, you know that, so because of the operator A0 is positive, by the min-max principle, it's clear that lambda n of beta are increasing functions with respect to beta square, which means that when you increase beta square, the spectrum moves like that, more or less. And so the solution of the problem is take u as one of the eigenfunctions. You take omega is plus or minus omega n of beta, which is the square root of lambda, called a beta mode. And the solution you obtain is something like that. And this is called the propagative mode because beta is real, so this solution oscillates in Z up to infinity, no decay. Omega equal omega n of beta is called the dispersion relation of the mode, of this particular mode. This ratio is the phase velocity, and the group velocity is the derivative of omega n of beta with respect to beta, and because of the monotonicity property in beta square of the eigenvalues, you can prove that this group velocity is positive for positive beta, and for this reason, this is called a forward mode. So when you look at the second problem, so you have a very similar situation. You have again a sequence of eigenvalues that go to infinity, but this time, since the operator is only bounded from below, not all the eigenvalues are positive. So you have again a sequence of eigenfunctions, and as I said before, the zero is somewhere. So there exists a finite number of negative eigenvalues. And this number depends on omega, and because this time the functions mu n of omega are decreasing function with omega square, the number of negative eigenvalues will increase with omega square. For instance, from this situation, if you increase omega, so the operator, the eigenvalues move like that, there is a threshold when one of these becomes zero, and after this threshold, a new eigenvalue, negative eigenvalue appear, and this continues up to infinity. Okay. So, and the solution to the second problem is to take one of the eigenfunctions un omega, and this type beta n omega, so because minus beta square is the eigenvalue, beta n will be real or imaginary depending on the sign of the eigenvalue. So for the negative eigenvalues, this will be real, and because this will be real, we have propagative mode as before. But for the infinity of positive eigenvalues, the beta n must be imaginary. Reason why the modes are called evanescent, because they are decreasing exponentially in one of the two directions. Okay. So just to illustrate this by dispersion curve, so for the first point of view, find beta, the functions of omega. So here I plot the functions omega n of beta, so it's not a real plot, it's an idea of what the dispersion curve look like. So there are an infinity of them that go to infinity, that go to plus infinity. They start at so-called thresholds that also go to infinity. And to begin to understand the other problem, given omega, find beta, you can choose a frequency, omega star, for instance, between the second and the third threshold. And you see that the line omega log omega star intersects only two of the dispersion curves at two wave numbers, beta 1 and beta 2. So you can go then next to the second point of view. So in that case, it means also that the number of propagative mode is 2. Okay. And in the second point of view, beta is a function of omega, so you can invert these curves to obtain this. So you recover beta 1 and beta 2 by this. And what you have to understand by looking at this curve is that as soon as omega is lower than the given threshold, for instance, lower than omega 1 for the first threshold, the beta n becomes imaginary, reason why you do not see it on the picture. So the horizontal line means that the corresponding beta has gone to the imaginary axis. Okay. So there is an even simpler case that we will meet, is when the operator A0 is proportional to the identity. So C is a positive constant. And in that case, because A1 is beta square, is C square, the eigenvalue problem can be written in a way where beta and omega play a very symmetric role. In fact, the eigenvalue is this time the difference omega square minus beta square c square, and you have only to take care of the spectrum of the operator A2. So this operator A2 is itself positive, definite, or positive and self-adjoint. So you have a sequence of eigenvalues. They correspond to the threshold of before. And then the solution for the two problems is simply U equal UN, so the beta mode and the omega mode are the same in that case. And the dispersion relation takes a very simple form because the eigenvalues was omega square minus beta t square. So for the first problem, this is the dispersion relation. And for the second one, this is the expression. So you see that the fact that the beta is real or not depends on the position of lambda n with respect to omega square. Okay. So as I said, the application to acoustic waveguide. So for acoustic waveguides, a good framework is L2 of S of the cross-section. You have to work with a weighted inner product, so lambda is the Lamé's coefficient here. And also, so you see, if I introduce the acoustic velocity, so there is a density of the fluid, so the acoustic velocity is given by this formula. It's easy to see that the operator is rigorously defined this way, so with the definition of the domain and then the operator, where you identify the part A2 and the part A0, so there is no A1. And you see that A0 is simply the multiplication by the function c square. So a priori, c square is a function of the transverse variable. Okay? The corresponding bilinear form is this one in the space V, which is H1 here, because consider the Neumann condition. And the fact that we are in the framework, the fact that the operator is compact is due to the fact that the embedding of H1 in L2 is compact. It's very simple. So it corresponds to the situation of the closed waveguide. And the last case, the last simplest case where A0 is proportional to the identity, you see it will be when the function C is in fact a constant. Okay. So it is the simplest case. So just to finish this first part, how it can be used for solving the time evolution problem. For instance, I have simplified by considering U0 as the only data of the problem. So what you can do is apply a Fourier transform in Z, so that each U beta function is 2D function U beta, this time satisfies this evolution problem where you make appear the operator A of beta. And to compute the solution, you can expand the solution on the basis of the eigenfunction. So you have only the coefficients which are real valued to determine. And each of the coefficients, of course, simply solve these differential equations, where you make appear the eigenvalues of A of beta. You solve this explicitly, very simple. And then you apply the Fourier inverse transform to the expression you obtain by after substituting the expression of un of beta. And what you get at the end is this expression. And you see that you can reinterpret it that the solution is a superposition of propagative eigenmodes, where this superposition is discrete with respect to the index n, and it is continuous with respect to the wave number beta. So any solution can be represented in this perfect solution with the help of mode. Okay. So second part of my talk, I attacked Maxwell's equation. I chosen to take time to give some background. So I recall that x and y as a transverse variable, easy is normal to this plane, and Yes, and if you consider a vector field which is in the tangent plane, I recall that taking the cross product with EZ corresponds to simply rotate the field in this plane. Moreover, if I consider a 2D scalar function phi and 2D vector field u, which is in this plane, so I recall the 2D gradient and divergence operator, and relatedly, I can also introduce two curls. A vector curl indicated with an arrow and a scalar curl. And in fact, these are completely directly related to the previous operator with rotations. So in the sense that, for instance, the vector curl is simply the rotated gradient, as you can see immediately. And the curl, the scalar curl of a vector field, is the divergence of the rotated field. A last remark, it's very simple, is that when you compose this operator in diagonal, you always obtain 0. For instance, the scalar curl of a gradient is 0, and the divergence of the vector curl is 0. Sorry. So now I introduce the cross-section S, and I recall the very well-known Green's formula with the grad and div operator, but that you can transform into a Green formula with a curl and curl operator simply using the rotation relationship. For instance, it suffices to apply the previous formula to the rotated field, and that's it. And that's why you see that the normal trace is replaced by the tangential trace, for instance, in the boundary. So from now, I will represent a vector field, a 3D vector field this time, as indicated here, with EZ is a longitudinal component, and E, bold E, I don't know, the transverse one. And even if it's defined in 2D, you can identify it to a field defined in the cylinder, making it invariant along Z, for instance. And from this, you can define the tangential trace on the boundary on S. I identified to the tangential trace on the boundary of the cylinder. And of course, this tangential trace has two parts. One which is tangent to the boundary of the cross-section along tau, and the other one which is a longitudinal one. So imposing this to be 0 means E tau equals 0 and EZ equals 0. So an important guy will appear, which is the operator curl beta. So with the terminology I have introduced before, the curl beta is simply deduced from the curl by replacing the z derivative that would appear here with the usual curl by I beta, and you get this expression. And this I've chosen to decompose. So relatedly, you can also introduce the grad beta, where the change is only in the last component, and the div beta operator. And from the relation before, it's immediate to check that the curl beta of a grad beta is 0, the del beta of a curl beta is 0. No problem. The curl beta is always 3D. There are only one curl beta. And here you can decompose as before. So the first part is the first transverse field, which appears to be simply the vector curl of the longitudinal component. The second part is the only one that makes appear beta. It is simply the rotated transverse field. And the last part is a longitudinal field, which is proportional to the curl, the scalar curl of the transverse field. Okay. So this I have recorded here. And using the previous Green's formula and this decomposition, it's immediate to obtain this Green's formula for the curl beta operator. And you see that as soon as these two traces, E dot 2 or EZ and EZ vanish, so the boundary term disappears. Okay. It's not easy to know which end I have to activate to change between the two. So now I go back to the model equation. So if you put this in the Maxwell's equation, you obtain this model equation involving the curl beta operator, all in weak form corresponding to this sesquilinear, the variational formulation. But up to now, it's again formal, so I need to precise in which functional framework I can do that. And so this is what I'm going to say. So as you can expect, maybe, you have to work in the space L2 to the power 3 with a weighted inner product associated to epsilon, to the permittivity of the medium. And so it's natural to introduce the H curl beta operator of vector fields in L2, whose curl beta is also in L2. And implicitly, it is an Hilbert space for the corresponding graph norm. But a priori, it seems to depend on beta, but if you remember the expression of curl beta, you realize that, in fact, it does not depend on beta because this is automatically in L2. And so this space is, in fact, comment on dit, product, this Cartesian product of H1 for the third component, because you remember that the curl is essentially a gradient up to rotation. And for the transverse component, it is a 2D H curl space of vector fields whose scalar curl is in L2. And if that you want to add the boundary conditions, so you have to work with the space H0 curl beta of subspace that satisfies the free boundary condition. And because this trace is like that, you see that it corresponds to take the product of H0 curl times H1 0. It is H1 0 for EZ because EZ must be 0 on the boundary. And it's H0 curl for the bold E because E dot 2 is equal to 0. So this is a so the bilinear form, the Hermitian sesquilinear form of the weak formulation of the problem is this one. And as usual, this bilinear form defines the self-adjoint operator, which is positive, because the bilinear form is positive, and of which I have given in detail the domain, but I will not spend too much time on this. It's essentially a curl beta operator with variable coefficients. And so if I look at the problem beta, the easy one, I'm going to look, beta given, you have again a self-adjoint problem, an eigenvalue problem for the self-adjoint operator A of beta, which is a positive self-adjoint operator. So if you compare acoustics with electromagnetics, so these are the bilinear forms, there are some differences. In particular, the fact that in the abstract expansion I have been given at the beginning, in electromagnetics, the A1 is non-zero. I will make precise this. And because of that, and Sophie will come back on this, the quadratic form associated to the operator is non-monotonous with respect to beta. And another difference is that we shall see that the resultant of A of beta is not compact as it was in the acoustic case. And by the way, we shall see that this operator has an infinite dimensional curl. So considering the first point, if you use again the expansion of curl beta, it's easy to obtain this expansion of the bilinear form in powers of beta. And you see that the second term, you see, this one is non-zero, and it is responsible for A1 to be non-zero. And the kernel of A of beta, it has an infinite dimension, and you can identify it as the space of the gradient beta of fields in H1 0, and as the proof is easy, I will give it. So first, the reverse inclusion. If you start from the gradient beta of a field in H1 0, so first, of course, as the curl of gradient is 0, so the curl beta of E is 0, which means in particular that E becomes to H curl beta. Because phi is 0 along the boundary, because phi is in H1 0, so E dot 2, which is tangential derivative of this trace, is also 0. And the vector field EZ, which is I beta phi because of the definition of grad beta, is also 0. So putting this together, you have E, which is in H0 curl beta. And of course, the curl beta is 0 because the curl beta is already 0. So this means exactly that the field we have constructed, is in the domain of the operator, and it is in the kernel, in fact, because its image is 0. And reciprocally, if you start from something which is in the kernel of A of beta, because of this formula, being in the kernel of beta implies that the curl beta of E is 0. But if you remember that, so these are the two first components of the curl beta operator. So you have these two equalities. So that if you define the phi that will realize the theorem as 1 over I beta times EZ, you see that from the second equation, EZ is simply the x derivative of phi. EY is simply the y derivative of phi, and beta is I beta by times phi by definition of phi. So you have proven that E is a grad beta. Okay. So once you know that you have an infinite dimensional kernel, it's so natural to introduce its orthogonal complement in the Hilbert space, so that with respect to this decomposition, you have a representation of the operator like that. And this side, I will be in the rest of the, interested by the restriction of this operator to this operator H epsilon beta, and I call it I epsilon of beta because the space itself a priori depends on epsilon, as we will see, because in fact it can be identified. This orthogonal of a kernel is simply the vector field whose divergence beta epsilon is 0. And this is completely immediate because being in H beta, so in the orthogonal of the kernel, means that you have this integral is 0 for any element of the kernel. And in the sense of distribution, it is exactly the fact that divergence beta of epsilon E is 0. Okay, so now the rest of the analysis will rely on results on 2D vector fields that I am going to give now. And I will begin by a negative result, is that the fact that the embedding of H curl into L2 is not compact, contrary to what we observe with H1. And for instance, to prove this, you can consider the sequence of eigenvalues of the Dirichlet Laplacian. And you consider a vector field which is the normalized gradient of the corresponding eigenfunction. So of course, the curl of E is 0 because the curl of the grade is 0. and it is bounded because I have normalized the eigenfunction. So it is bounded in H curl, and however, it has no convergence subsequence because two different gradients are orthogonal. So two elements of the subsequence are orthogonal in L2, so it can have a strongly convergent subsequence. And as a consequence, the bigger space H1 zero curl beta is not compactly embedded, and the reason of the lack of compactness does not come from the longitudinal component, because this embedding is compact, but from the transverse component, because this one is not compact, as said before. Yes? It was H0. It was H0 curl because I took the Dirichlet equation. Okay. But of course, if H0 curl is not compactly embedded, a bigger space is not too sure. But you're right. So the next two results will provide a kind of reciproc of the fact that if the divergence of a curl is zero, is there a reciprocal? And so I will give successive lemmas. So first one, it is true in L2. So if you have a vector field in L2 with divergence is zero, then U0 is a curl, vector curl of a H1 function. And then for the next result, I suppose that S is simply connected. This is important. And the second result, you go from R2 to S, and the results remains true in the simply connecting case. So a function with free divergence is a curl of an H1 function. And as a consequence, we have the so-called Helmholtz decomposition of vector fields. The fact that any L2 vector field can be decomposed as the sum of a gradient plus epsilon minus 1 times a vector curl. So epsilon minus 1 is just for the means of our application. And from this three lemma, we shall prove, so I give the proof of everything, that this time the embedding of H curl 0 with H div epsilon, where H div epsilon is a field of vector fields whose divergence epsilon is in L2, then you recover compactness. So for getting compactness, you will need a control of the divergence, and also the fact that you take the boundary condition is important. If one of these two is not satisfied, compactness is lost. So the first lemma in R2, so this is easily done in Fourier transform. So you consider a function which is compactly supported. And so its Fourier transform is C infinity, of course, because and in L2, because initially it's in L2. Voilà. So this is the reason. And the divergence condition is simply this algebraic condition, which means that these two fractions here are equal. And if they are equal, I can give a name, psi 0 hat. And you will remark that if you express this equality for psi y equals 0, you see that ux is 0 along the image, the axis, the real axis in the psi x psi y plane. And what I say is that this function is in L2. Now, the reason why it is in L2, it is because if you take a psi in this square, here, in the unit square, you can use a Taylor expansion from the real axis And using this Taylor expansion, because it is 0 on the blue axis, you have this estimate where in psi y. So if you use the fact that psi is u divided by psi y, you see that in the square, the psi 0 hat is bounded. And outside is bounded by this quantity. And outside, I say that either psi y or psi x is bounded from below. So necessarily, you see that psi 0 is less than some constant times ux squared or uy squared or the sum. And because of these two components, because it is bounded locally and bounded by an L2 function globally, it is in L2. So this is this function is in L2. And finally, so if I introduce psi 0 as an inverse Fourier transform, and these two relationships which are a consequence of the definition of psi 0 means exactly that U0 is a vector curl of the psi 0, and which proves that psi 0 is also in H1 because its curl is in H2. So the proof is complete. Now, the second lemma is says that the result remains true in a simply connected domain. And the proof is to use the previous one by extending U to some U0 in R2 and applying the previous lemma. So this is the domain. So I consider a bigger ball that encloses S, and I call the omega the difference between this ball and S, and the exterior. And to construct my L2 field, my compactly supported field, so I will take U0 equals 0 outside to be compactly supported, U0 equal U inside to be an extension, and I just have to fill things in between. And of course, by construction, you have the divergence 0 condition is already true inside and outside because it is in the assumption. And to fill it, you build a joining as a gradient. So, and a gradient is automatically curl-free, by the way. And you will ask to theta to be a solution of the Neumann boundary value problem in the domain omega, like that. So by construction, the divergence of theta will be of the gradient of theta will be 0. And also to ensure that the divergence is in L2 across the interfaces, you have to ensure the continuity of the normal component of the field, which corresponds to impose these two Neumann conditions. And the important thing is that this Neumann problem, because the domain is connected, is well posed because the compatibility condition that you know that you need for solving Neumann problem is satisfied because the divergence of U is 0. So everything is okay. So once you have done that, you know that the extended function is the curl of the psi 0 and is sufficient to take the psi of the answer of the theorem as a restriction of the psi 0 to the domain S. Okay. So from this, you define the decomposition lemma. The proof this time is easy because first you assume that so any U can be expanded like that. So if it is true, you see that the epsilon U minus grad phi multiply is a curl, so its divergence is 0. So it means that necessarily phi, if it exists, must be solution of this Dirichlet problem. So you take this solution of this Dirichlet problem. By construction, it has divergence 0, and by lemma 3, by lemma 2, it is a gradient of the psi. And then you get the proof, and this is finished. So it's clear that because you take a curl that psi is unique up to an additive constant. It is also so you can impose that the field is in the space H1 circ of field functions with mean value 0. And another remark is that the decomposition is in fact orthogonal for the weighted inner product. And this is due to the fact that if you consider the cross product that would appear in taking the square of u, in fact, it is 0 by Green's formula. Curl and the grade are automatically orthogonal. Okay. So, in fact, these three lemmas, the lemma 3 simply says that we have an orthogonal decomposition of L2's field as the gradient of H1 0 plus epsilon minus curl of H1 circ. But this is true for simply connected case. Okay. And I can conclude to the compactness result I announced. So you consider a sequence which is bounded in this space, which means that all these quantities are bounded and plus the boundary condition. And then you apply the decomposition of vector field to this UN here. And you use the orthogonality conditions I have mentioned before. And because this is bounded, it means that each of these terms is bounded. But for each of these terms, you can use a Poincare inequality. So they are bounded in H1. And so they have a subsequence which converges strongly in L2. So this is the first step of the proof, up to changing to passing to a subsequence. Then I will show that U is a Cauchy sequence. I introduce the differences and the corresponding Helmholtz decomposition. And I take the cross product of this by UPQ, and then I integrate. And you get this. And this is finished because if you apply a Green's formula to the first part, you make appear the divergence of UPQ. And then this time everything is OK because so there are two Green's formula. Okay, for each term I have used Green's formula. And so in the second term, it's nice because you have one term which is bounded and the second term which converges strongly to 0. Okay? Okay, this is bounded. And this goes to 0, so the cross product goes to 0 and PQ goes to 0. And the proof is finished. So as a consequence of this 2D compactness result, I claim that the intersection of the space H0 curl with the space of divergence beta equals 0 is also compact, and it remains very simple because so you remember that this curl beta space is this product. So if you take a sequence which is bounded in this product, of course you only need to look at the transverse field because H10 is already compact in L2. But you have to use the free divergence condition. And the fact that you have the free divergence condition means that divergence epsilon un is given by this. But since this is bounded, divergence epsilon un is bounded. So if this is bounded in a zero curl and the divergence epsilon is bounded, it means that you are bounded in the space here. And because the space is completely embedded in L2, you conclude. Okay. So this finishes the technical part of the talk. And once you have this, now when you look at the restriction of the operator to the space A beta, you are back to the situation that we got in the acoustic case. You have a self-adjoint operator which is positive with a compact resultant. So it has a sequence of eigenvalues that goes to infinity with an orthogonal basis of eigenmode. And the solution to the guided wave problem consists in taking E proportional to one of the eigenvectors and omega n given by the dispersion relation, as in the acoustic case. Okay. Mais tu sais pas ce qui vient. And Sophie will give some complement to the results I have given here, but I just want to finish by addressing two relevant questions. First, you remember that there was a simplification in the acoustic case when the acoustic velocity was constant. Is this true in the electromagnetic case? And second question, what are the changes when S is not simply connected, in which case we speak also of coaxial cable. So very quickly, for answering the first question, I will propose an alternative formulation. There are many formulations of the problem, this is one of them. Concerning the transverse field. So here, I have rewritten only the projection of the modal equation of the transverse plane. And then I will eliminate the field EZ by using the divergence condition, you see? Using the divergence condition, you can eliminate in terms of E, and you see that you get an eigenvalue problem only with E. And it seems to be very simple and more simple than before because you have no beta here. You have only beta square and omega square. So it seems to be very nice, except the fact that, in fact, the operator that you have is not symmetric. You see, in fact, this one is, the first one is symmetric, but maybe you can, see, this one is symmetric, if you may. But this one is not because of the function c square. However, if c square is constant, for instance, if it is 1, then you recover symmetry on both those operators. So what you can do when c square is a constant, you can simply divide everything by c square, and you reconstruct a problem in which, as in the acoustic case, you have a nice symmetric self-adjoint operator, and the eigenvalue is again omega square divided by c square minus beta square, and this is the corresponding weak formulation. And in operator form, you can rewrite it as a self-adjoint eigenvalue problem that does not depend on any parameters. The parameters are in the eigenvalue. And the self-adjoint operator is formally the sum of a curl, yes. You have to divide by epsilon minus 1. And so it is this curl operator plus this grad div operator. So you have these two operators. So remembering that what I said before, that the space of the Helmholtz decomposition, the space H of L2 vector field can be written as the sum of the orthogonal sum of the images of H1 circ and H1 0 by the two first order operators, which was epsilon minus curl and gradient. So and remarking that here you have an epsilon curl for these are the two operators. The fact that you have an epsilon minus curl here and here proves that, in fact, A1 maps H1 into itself. And it is the same for A2. So in fact, you have an orthogonal decomposition of the operator. It's not only a formal sum, and as a consequence, the spectrum is the sum of two different spectra. So this is a picture that summarizes what I have said. So you see H1 as the images of scalar field, the space of scalar fields, either by the epsilon minus curl or the gradient operator. And these are the two operators I am interested in. So I can construct the first family of modes from the operator A1, and this will be the transverse electric mode. And the idea is to start from the Neumann mode of this scalar problem. And I eliminate the eigenvalue 0 because I restrict to field with mean value 0. So you know that they exist. And from this, I am going to construct, this divergence gradient operator, I can already rewrite it as a curl-curl. It's exactly the same. Okay? And I introduce W as the epsilon minus 1, the curl of any eigenfunction. And I claim that it will give an eigenfunction of the vector operator A1, because since you have that, it means that by definition of W, you have that. And if you apply again the epsilon minus 1 curl to this equality, you get this. But by definition and this is exactly omega squared UN. Okay. In addition, the fact that you have gradient psi dot nu is equal 0 and Wn is a rotated gradient, you obtain the good boundary condition. And all of this, you conclude that because of the definition of A1, you have built a basis. You have built a set of eigenfunctions for the operator. And what I will not do, but it's not so difficult, is that you can prove that the corresponding fields after normalization form an orthonormal basis of H1. So it means that, in fact, I have completed the diagram below by a kind of commutative diagram. In some sense, the vectorial operator A1 is equivalent to a scalar operator A1, where you have simply inverted the vector and the scalar curl in the definitions. By definition, from what I said before, the corresponding guided mode is given by this expression. You have a very simple dispersion relation. And if you remember the divergence condition, but this divergence, because epsilon E is a curl, but you deduce that the EZ is 0. That's why we call of a transverse electric mode, because the transitional field is 0. So for the second family of mode, I can accelerate a little bit. It is the same, essentially. So the scalar mode that you have to introduce, it seems very similar to the phi, very similar to the psi, except that you see that you have interchanged the role of epsilon and epsilon minus 1. So when it is constant, it's both a Laplacian operator. And we use a Dirichlet condition instead of a Neumann condition. But you obtain the modes by taking the gradients. It's exactly the same picture where gradient replacing epsilon minus 1 curl. And you form, this form an orthonormal basis of A2. And looking at the field, this one, you don't look at qualify them, you don't look at the electric field, but at the magnetic field, which is proportional to the curl of E. But the curl of E, since E is a gradient, it is 0. And this is why we call them transverse magnetic. So to finish, what happens in the non-simply connected case? Combien? 1 minute. But it depends on the length of the minute, of course. We are in Marseille. So no, I will try to do. But I have a kind of joke at the end. So you cannot miss this. So there is some holes in the, and what changes is that the decomposition of 2D vector field has to be modified. In fact, in the decomposition of vector field, you see that there is a new guy that appears, and it is called the fields of electrostatic field, which are both curl and divergence epsilon free, while satisfying the boundary condition. So in the simply connected case, this space is 0. But in the non-simply connected space, this space has the same dimension of the number of holes. And it is spanned by the gradients of a family of solutions of boundary value problems in S, which are solutions of a Dirichlet divergence epsilon grad problem, where you have a 0 trace on the exterior boundary, and which is not classical, particular, are the boundary conditions on the boundary of the holes, and which is given like that. And for instance, for phi1, it means that you will ask to phi1 to be 1 on the boundary of omega 1 and to be 0 on the other boundary. Of course, you define as a field which is not constant, so the gradient is not 0. So I will not, the proof is not so difficult, but I will not give it. And, but concerning the compactness result that was at the basis of the theory, nothing changed because this new space is a finite dimensional. Compactness result still true. But there is an interesting change in the case of constant velocity, the last case I have presented today, because you have this equation. So this, as the operator is this operator, this time this operator has a kernel, because you have in a non-simply connected case, and this kernel is exactly, as you see, to be 0, you need both curl and divergence is 0, and this kernel is generated by the static fields. And so in addition to the TM modes I have presented before, which are still there are an additional family of transverse electric and magnetic modes, because both electric and transverse fields are 0, which are given by the gradients of these additional fields. And because they correspond to the eigenvalue 0, they correspond to what I call a non-dispersive dispersion relation. These are the TM modes. And both EZ and EM to 0. And tu me laisses me faire mon... J'espère. Bon, j'avais une preuve en plus, mais Ah, non, mais là, ça sera 30 secondes. Mais c'est là... it is the best part of the talk. Merde. Thank you for your attention.
Thanks to you for this very pedagogic talk. But in order to respect the schedule, we have no question, but you can speak with.
Can you tell us the score of the last match between Paris and Marseille?
I don't remember. My memory is not gonna.
Perhaps one question.
Ah, ça y est, on l'a eu.
No. Yeah.